In this video, we present our latest work on mapless navigation using an SDF-based neural NPC. We address the problem of achieving collision-free navigation while relying only on instantaneous onboard range measurements. Our method relies on a mapping of a single range measurement into a volumetric representation that captures the free space within the currently visible frustum. To approximate such mapping efficiently, we employ a two-stage neural network. The range image is first encoded into a low-dimensional latent space. Then an MLP approximates the SDF value conditioned on the environment encoded in the latent vector. The neural SDF is an analytically differentiable representation, enabling direct integration in a gradient-based NPC as a collision avoidance constraint.
First, an ablation study is performed in two different settings: pillar-filled environments that effectively reduce the problem of obstacle avoidance to 2 dimensions, and 3D environments with obstacles of arbitrary size and shape. We perform 200 rollouts in randomized environments for each set of parameters, while recording the average rates of success, timeout, and collision. This allows to assess the sensitivity of the method to environment settings and hyperparameters, such as the reference navigation speed or the obstacle density. In a second step, the proposed controller is compared with state-of-the-art local navigation methods in the Avoid bench simulator. We evaluate the performances for all methods in 32 randomized environments, using metrics such as success rate, average speed, and path optimality. The environments are parametrized using a traversability metric that describes the obstacle density along the trajectory. In this experiment, the robot uses a constrained field of view depth camera for navigating in a forest environment. On the bottom right, a top view of a horizontal slice of the neural sign distance field is displayed. The visualization shows how the predicted trajectory deflects from the reference velocity to avoid collisions, since the NPC is constrained to operate within the blue level set. We use the 360-degree LiDAR for collision avoidance in this experiment. The adversarial reference velocity is provided by a human operator. At the beginning of the trajectory, the operator sent the robot towards a wall-like obstacle. In response, the NPC brings the robot to a full stop, as there is no nearby free space that could accommodate the velocity reference. In the remainder of the experiment, the operator provides unsafe references, actively trying to collide the robot with tree trunks, branches, and bushes. The neural SDF representation, shown in the bottom right, clearly illustrates how the predicted open-loop trajectory is deflected from the obstacles by the position constraint, pictured as the blue level set. We perform a simulation study to quantify the resilience of the method against several levels of position drift. The drifting position is retrieved through integration of increasing noisy velocity and quantified using relative position error. We perform several rollouts in each setting and assess the success rate of the method. Additionally, real-world experiments are conducted to support this ablation study. We use the 360-degree LiDAR for collision avoidance and use the FMCW radar and IMU for velocity estimation. The system position is retrieved through integration and therefore drifting with a relative position error of around 3%. The green odometry represents the true position in the map as computed from the LiDAR data for visualization purposes. The red one is the drifting radar odometry provided as an input to the Nonlinear NPC. Because it relies on instantaneous range observations and operates in the local frame, our method safely navigates despite the position drift of more than 1 meter at the end of the trajectory.